This is the third video involving complex numbers of polar coordinates and DeMoivre's theorem. And probably I would give this during the second class on this topic, which is, I guess we would call it class number 15. So I'd like to start with a few problems off of this worksheet, all right, which is on Blackboard. And we'll just do a couple things here. Okay, let's pick Z1 is 1 minus 2i. And one of the questions we're asked to do is compute this. Okay, so I think this is question 2a on that worksheet. And, we're asking for the modulus. So this is your a and b is -2. So what you're basically going to do is 1 squared plus -2, the quantity squared under radical. And you're going to get that the modulus, this is actually the value of r here is going to be square root of 5. Okay, so it's not so bad. All right, if we go on to question 3 in that problem set, they asked us to do a little bit of graphing. So let's try D, which says make a sketch of this. Okay, so this type of set builder notation it's called. This means such that. So in this case, we're asked to do a graph of all the complex numbers z such that the modulus, or actually the r value, is less or equal to 2. So what that basically entails, okay, is we're making a sketch here. Okay. And this, of course, would be 2i, but it's actually a radial distance of 2. Okay, so all those points are radial distance of 1. All these points are radial distance of 2. And what we're asked to do is make a sketch of everything which is 2 or fewer units away from the pole. So that would include the actual edge of the polar circle and all the points in between. So this would be a filled in disk with a boundary. Okay, so that's the kind of stuff you should be able to do without too much difficulty. Okay, let's move on to some of the actual computations now. And the first one we want to do is going to be a multiplication. All right, so multiplication using DeMoivre's theorem. Okay, so let me make some space here to work. This doesn't erase too well, but all right. All right, it's coming out okay. Okay, so the first problem is to do a multiplication. And the problem will be multiply uh, 3 cosine 20 plus I sine 20 degrees times 4 cosine 70 degrees plus I sine 70 degrees. Okay, now in this case, we're going to be using the multiplication version of DeMoivre's theorem. And the rule is, well, this would be like our Z1, this would be our Z2, and the rule is Z1 times Z2 is, oops, parenthesis goes here, sorry. Okay, is R1 times R2, cis theta 1 plus theta 2. So when we multiply, we're basically using the laws of exponents on the arguments or the angles, and we're adding them. Okay, and we said the reason for that is because these are really r e to the I theta. Okay, it's a little more advanced, but okay, so in this case, the R1 and the R2 are 3 times 4. And since these are already in polar form and cis form, if they weren't, we'd have to do a conversion. Since they're already in cis form, all we're going to do is, well, the rule says add the angle. So you have 20 and 70 is 90. So this would be 12 cis 90. Okay, and we can work this out, so that's what we're going to do. Okay, so 90 degrees is right here. Okay, so you have cosine 90 plus I sine of 90 degrees. And the cosine of 90 is, as everybody knows, well, just make a little sketch here. Cosine of 90 is 0. And the sine of 90 is 1. So this is 1i. So you get 12 times 1i. The final answer would be 12i. Okay, so that's kind of a pretty easy question. And using our form of DeMoivre's theorem. So let's go ahead now and let's do a division problem. Let's see if this works better. Yeah, seems to work a little bit better. All right, so we'll have to do a division problem. Working too well. This is the best. Okay, division, here we go. Divide. 12 cos 180 plus I sine of 180 divided by 4 cos of 45 plus I sine of 45. Okay. See if I copied correctly. I think I did. Okay. So the rule is, okay, if you're looking at this, you have Z1 divided by Z2 is R1 over R2, cis theta 1 minus theta 2. So again, it's very much like applying the rules of exponents because that is what is going on here behind the scenes. Okay, so we simply divide out these values. That's a 3. And then this would be cis 180, cis 45. We do a subtraction, cis 135. And that's basically the answer. And now we're just going to spend some time and sort of get this into more palatable form. Perhaps the instructions will say A plus BI form, in which case this really doesn't qualify. So we go 3 cosine 135 plus I sine of 135. Okay, and now we're going to work out each of these. So here's what I'm going to do. I'm supposed to know 135 degrees is in quadrant 2. Okay, we know the reference angle is 45, and that makes a 1, 1, radical 2 right triangle. Okay, this of course would be negative. All right, so the cosine of 135 is negative 1 over radical 2. It's adjacent over hypotenuse. Okay, we can fix this up later. In fact, we probably will. And the sine of 135 is 1 over positive 1 over radical 2. So let's fix this up a little bit because often the book will have the answer in simplest radical form. So I've got 3 negative rad 2 over 2 plus I rad 2 over 2. And when I multiply by 3, I get negative 3 halves radical 2 plus I 3 halves radical 2. Now you could put the I on the end here. The only difficulty with that is often people are a little bit careless and they think the I is under the radical, which of course it's not. Okay, now just a little bit of an explanation. We're typically not going to get the problem in this form, okay? What we're typically going to do is we're typically going to see it in a different form. So the cosine of 180 is negative 1, sine 180 is 0, so this might be negative 12, right? Because cosine of 180 is negative 1, and sine of 180 is 0. So the top of this whole fraction is really negative 12. And cosine of 45 is rad 2 over 2. And sine of 45 is rad 2 over 2. And when you multiply by 4, you get that this bottom is really 2 rad 2 plus 2I radical 2. So the question could have been written like this. Okay, so if the question were in this form, you'd have to take the extra step to put it in complex polar form, which really is a cis form. Okay, so that would have been a more involved problem, really the exact same thing. Okay, so let's go ahead and do one more, which is a product. Okay, I'm going to see how this comes off. Well, let's pause this for a few moments. Okay, I cleaned up the board and we're ready to go for the next one. Now, pi over 5, pi over 10 are not convenient. This would be 18 degrees, and this is 36 degrees, right? 180 over 5 is 36. Not convenient. So, but that doesn't mean that we can't get some sort of an answer, and we can always put it in our calculator later. Okay, so let's suppose we're doing a multiplication here. 3 times 4, well, let's just go over the rule again. You multiply the moduli, and in cis form, you add the arguments or the angles. Okay, so in this case, 3 times 4 is 12. That's easy to do. And you add the angles. So you have pi over 5 plus pi over 10. The LCD is tenths, of course. This is 2 tenths, and 1 tenth is 3 tenths. You get 3 pi over 10. So you get cis 3 pi over 10. And, if you had to write it out in the longer form, you would say 12 cosine 3 pi over 10 plus I sine 3 pi over 10, of course, with the parentheses. And if you wanted to, pi over 10 is 18. 3 times 18 is 54. You could also write it in this form. So again, this is pretty easy stuff, and there are different versions that we could try. The next bit of topic is a little bit more interesting. It's multiplication. Okay, so I'm going to pause the video and erase this, and we'll come back. Okay, we are back. Let's try a multiplication, and let's just do a review of, not a multiplication of power, so let's do a review of the power rule. Okay, if z equals r cis theta, and this time I'm not doing the z1 to z2 because I'm just raising a single complex number to a power. Then z to the n is r to the n cis to the n theta. Cis n times theta, rather. All right, so we talked about this. It's like power of a power dealing with exponents. There is a sort of a proof on Blackboard, and basically what happens is multiplication is repeated adding. So let's suppose we had z to the first will be a 1n, z to the second, you get theta plus theta would be a 2 theta, z to the third would be a 2 theta plus 1 theta, we're adding angles is 3 theta. So doing that a few times, noticing a pattern, this is the rule that we're going to end up using. Okay, so the problem that I would like to do is radical 3 minus I to the 6th power. Okay, so this is example maybe number 5, I'm not sure. And this is the kind of problem that appears on that DeMoivre's theorem exercises. This appears problem number 6. So now you should be able to do everything from 1 to 6. Okay, so let's give this a shot. Now, a little bit of a step up in level of difficulty. We need to compute r and we need to compute theta. So here we go. Let's start with our little diagram here. And this is the imaginary axis. This is the real axis. So radical 3 minus 1. So we construct our triangle like this. This would be radical 3 is the real part, and negative 1 is the imaginary or the I part. Okay, Pythagorean theorem says this is a 2. So we're back to our world of 30, 60, 90, because in a 30, 60, 90, the side opposite the 30 is half the hypotenuse, and therefore this must be a radical 3. So everything is working out nicely. Since we are in quadrant 4, the angle is really 30 shy of a full rotation, so it would be 330 degrees. And this, of course, is our value of r, right? It's the length of the radial side. So therefore, what the problem is saying is it's saying that what we want to do is we want to take 2 cosine of 330 plus I sine of 330 degrees, and we want to raise that whole thing to the 6th power. Okay, and what DeMoivre's theorem says, okay, is we take the modulus, which in this case is 2, and we raise that to the 6th power. And then we take the argument, which is the angle, and what do we do with it? We multiply it by the power. We multiply it by 6. So 330 divided by 6, multiplied by 6 rather, 18 carry 1, 1980. So you get, I'm going to shorten this up a little. Well, I can write it out a long way. Cosine 1980 degrees plus I sine 1980 degrees. And that basically is the answer. What we want to do is we want to fix this up a little bit and see what this really is. In fact, we're going to come out with a nice expression for this, as you'll see. Okay, so this is more than a complete rotation. So what we need to do is we need to see not how many times it goes around, but where it ends up when it's done. Okay, so that means I'm going to take 1980 and I'm going to divide it by 360. Let's see if I can do that in this room allowed here. So 1980 divided by 360. So 5 times that would be 1800, I believe. So 505, I'll carry a 3. Yeah, okay, so in other words, have 1980 degrees, we would go around completely 5 times with a leftover or remainder 180. So this becomes 2 cosine of 180 plus I sine of 180. Right? Because it doesn't matter how many times it goes around, it's the final angle that we have. It's just like here. This was a negative 30 or 30, one around once was 330. It's the same type of thing. Okay, so this we need to work out. And 2 to the 6th is 64. And cosine of 180, whoops, negative 1. And I times the sine of 180, well, that's a 0. So this is 0 drops out, so you get 64 times negative 1, or negative 64. So this crazy thing raised to the 6th power, which would be really, really hard to do by hand, you could do it on the calculator. But the instructions would say, do it using DeMoivre's theorem, and then put in some sort of standard form. That would just be negative 64. Kind of amazing. So this is where DeMoivre's theorem really shines through, doing powers and roots. So we will do another power, and then we'll attempt to do one root, and we're going to really concentrate on doing roots in the video after this. I want to keep these a little shorter. Okay, so I'm going to pause the video, and when we come back, I'm going to do another example. Okay, here we go. This is our last power example, and it's kind of similar to the last one, but we're going to get a very different result. So the idea is radical 3 plus I is our z. We want to raise it to the 8th power. So what we're going to need to do is we're going to need to write this in complex polar form. So we make our diagram, and radical 3, this is the real axis, and the imaginary axis. Radical 3 is out here, plus I. So this is going to be in quadrant 1. And again, we have a 30, 60, 90 right triangle. And right, because the B is a 1, we're going up on the imaginary axis 1, and radical 3 is your x. Okay, so let's rewrite this in polar complex form. So radical 3 plus I is 2 cis 30. Okay, now I could have written cis 30, but I've got a little more room. I'm going to write it out. Okay, so now what I want to do is I want to raise this to the 8th power. Okay, and the rule is that we just talked about. Let me write it down again. Z to the nth is R to the n cis n times theta. So we raise the modulus to the 8th power, and the actual theta here is 30 degrees. What we would do is multiply that by 8. So 8 times 30 is 240. And this is our answer. This is what we have to work out. Okay, so 2 to the 8th power, well, I think it's 256. I believe it is. You can check me on that. Okay, so 2 times 2 times 2 times 2, 2 to the 4th is 16, and then 16 squared is 256. Okay, and now what we need to do is compute cosine and sine of 240. So I've got some room here, so I think what I'll just do is I'll do it in a different color so it stands out a little bit. 240. Let me make some more room here. Yeah. Okay. 240 degrees gives us a reference angle of 60. So 1, 2, radical 3, And because of the quadrant, we are in quadrant 3. This length will be negative and this is positive. So this is your 30. 30, 60, 90, side opposite. 30 is half the hypotenuse. That's your radical 3. And so let's go ahead and compute now. Cosine of 240. This is our 240. Adjacent over hypotenuse, negative a half. That should make you happy. And sine of 240, opposite over hypotenuse, negative rad 3 over 2. So what we're going to do is we're going to multiply this out now, get some simplification, right? Half of 256 is 128, but that's a negative. Okay, we got a negative here. And so you get minus 128i radical 3. Okay, so that would be the answer. And, you know, this is something that we did in only, say, a minute. And if you actually tried to raise this thing to the 8th power, I mean, that's insane. You would not finish, and you'd most likely make a mistake. Okay, one more example. Just to give you an idea of what's coming, we're going to take a root using the rest of the last part of DeMoivre's theorem. So I'm going to pause the video, I'll get this cleaned up, I'll put a new problem up, and this will be the last one. And at that point, you should be able to do on that DeMoivre's theorem worksheet, you should be able to do everything in the first 6 problems. Okay? If you want to go ahead and try the root problems, that's okay, but I'm going to spend another video on the root problems. So let me pause this. Okay, back again. This is the last example in this video, but it's the first one that we're going to do, which concerns with finding roots of complex numbers. This is by far the most interesting and useful part of DeMoivre's theorem. I guess that's a euphemism for being a little bit difficult, but let me write it out for you. Z equals R cis theta, and again, this means R cosine theta plus I sine theta with the R out in front multiplying. And the rule is we take the nth root of the modulus, and we take the actual theta, we divide by n, and then we add multiples of 360 over n to those. So what happens is we end up getting actually n distinct complex roots. If we're a 3rd degree, we get 3 distinct complex roots. If n were a 5th degree, we would, if we're taking a 5th root rather, we would get 5 distinct complex roots. Now, if you take a look at this, there was a slight mistake. In the last video, I started at 1. That's not correct. We started 0, and, oops, sorry, when k equals 0, this is a k now. When k equals 0, this doesn't appear. So you get the first of your complex roots is theta divided by n, and then you add multiples of 360 over n. So what happens is the roots are going to be equally spaced out on a polar circle with radius nth root of r. Okay, so the first one I want to do is the following. Find the 3 cube roots of negative I. Okay, so since we're doing cube roots, there are going to be 3 of them. So let's see how we set this up. The first thing to do is to find out what z is. So z is 0 minus 1i. Okay, and if you think about that, right down here, negative I, so that would be a R value of Well, what's the R value of that? 1. It's 1 unit, so R is a 1, and the angle, theta, is 270. So what we're trying to do then here is our Z is 1 cosine of 270 plus I sine of 270. Okay, this is our Z. And what we're going to do is find the cube roots. Okay, so here we go. So the cube roots of Z. Okay, there are going to be 3 of them. So I'm going to set this up. Okay, there are going to be three of them. And we're going to take the cube root of 1, because the modulus is 1. Okay, and the rule is you divide by the roots that you're taking. So you take 270 and you divide by 3. So that's going to give us cosine of 90 plus I sine of 90. So this is going to be the first of our complex roots. Okay, so think about this. You have 90 degrees, and what we're going to do is these 3 roots are going to be spread out, in this case, on the boundary of a polar circle with equally spread out. So if you take 360 and you divide by 3, we're doing cube roots, then we're going to get a cube root every 120 degrees. So let's make our little diagram here. Okay, so this is 90, and then we're going to get 120 more than that. So 90 and 120 is 210. So this is 210 degrees. So this is the point then, 1 comma 90 degrees, because the cube root of 1 is 1. This is 1 comma 210 degrees. And if I go 120 more, 210 and 120 is 330. So those are the 3 roots. It's the values of these complex points. Okay, so that's kind of cool, is they're spread out evenly about a circle in a complex plane with radius this, the cube root of the modulus, which is 1. So that's going to be the first one. And the next one will be the cube root of 1 again, cosine, 210 plus I sine of 210. And the third one will be right here. It'll be the cube root of 1 cosine of 330 plus I sine of 330. So those are the 3 cube roots of negative I. And what we're going to do is we're going to work them out, each of them. Okay? So let's see. Here we go. First one. The cosine of 90, well, this is sort of basic stuff. I'm running out of a little bit of room here. Cosine of 90 is 0. So this is a 0. The sine of 90 is a 1. So you get 1 times 1i. So I, or 1i, is one of the cube roots of negative I. We'll check that in a little while. So let's go down to the next one. Next one, this is a 1. Okay, so now we need to get the cosine of 210. All right, so let's see if we can do that. Reference angle is 30. So you have -1, 2, negative radical 3. And the cosine of 210 is negative a half. And the sine of 210, oops, I apologize, negative rad 3 over 2. Sorry. Cosine negative rad 3 over 2. And the sine of 210 is, that's the negative a half. And it's got an I in front. So when the smoke clears, what do? You get negative rad 3 over 2 minus 1/2 I. And that's the second of our complex cube roots of negative I. Okay, let's do the third one. Third one is cosine of 330. And again, it's the same thing. This is a reference angle of 30, negative 1, 2, radical 3. So let's go through the steps. This, of course, is a 1. Okay, so the cosine of 330 is adjacent over hypotenuse, so it's rad 3 over 2. And the sine is negative a half. And when the smoke clears, you get rad 3 over 2 minus 1/2 I. And those are your 3 cube roots of negative I. All right, let me check one of them. And I'm just going to check this one. But these you can check easily. In fact, there's a way to do this on your calculator. So I'll leave that up to you, or maybe we'll cover that next time. But let me just check one of these, okay? So I'm going to make a little bit of room here. So if you wanted to check the easy one, I don't have room to check the other. In fact, I'll check one of these next time. If you wanted to check negative I cubed, this would, sorry, not negative I cubed, I cubed, right? You would have I times I. This is a negative 1, and a negative 1 times I is negative I. So we just demonstrated that, in fact, if I cube this, I do get a negative I. Okay? So we're going to pick this up next time. The important points are what this means in terms of our picture. The fact, in this case, there are 3 of them. They are unique. And we're going to pick this up next time. In fact, we'll start with checking one of these. Let's say we'll check this one next time. And I'll show you how to do it on the calculator. All right, so signing off for now. And you should be able to do on that worksheet, you should be able to do the first 6. And if you want to experiment with number 7, which is the polar roots, be my guest. Thank you.